So, welcome to the next revision video on tectonic hazards, and the first video looked at the plate tectonic theory, and the next this video will be looking at 3 plate boundaries. The 3 plate boundaries you have to know, and they are specified in the specification. They're on there, they're listed, we know what's going to come up. So if we move these away and come back to this idea that there are 3 plate boundaries that you need to know about, and we'll take them one at a time. So number 1, this is the constructive plate boundary. And if you think about it, the word constructive sounds as if something's being built. It's construction sites. This is the plate boundary where new crust is being created. New crust is created here. Okay, so this is the plate boundary where we see 2 plates pulling apart. So the plates are together and very slowly they're pulling apart. And if we think about that diagram that we created in the last revision session, they're happening at this point here. So as the rock is rising and then is forced to the side, the crust above is pulled apart, creating a gap through which magma rises. So let's have a drawing. If we think of 2 pieces of crust, and there'll be kind of this sort of shape with a bit of a ridge in the middle. This piece of crust is going this way, this one's going this way. Let's get the convection current in underneath. Convection current, currents plural, as they move in opposite directions. And as these plates pull apart, this crust that's being created is oceanic crust. Both are the same. And as they pull in opposite directions, this warm magma, this melted rock underneath, can rise up through the gaps created to form, what do you think? Correct, volcanoes. So we are going to see volcanoes in this situation. And as that magma rises up and is erupted from the volcano, it then goes hard and creates new crust, which then splits apart. More magma rises up, fills the gap, becomes hard, new crust splits apart. And in this way, crust is created here. So this crust was created many millions of years ago. This was created more recently, more recently, more recently, most recently, right in the middle. So let's have a little think about these volcanoes. So the volcanoes that form here are shield volcanoes, and you do need to know that word. You will be expected to know it in the exam. And they are really gently sloping volcanoes. So you wouldn't necessarily identify it as a volcano if you think about the kind of traditional volcano that we see with the steep sides. This is not like it at all. And it is made of many, many layers of very thin and very expansive magma flows. So the magma has risen up from the magma chamber underneath. It rises up and then flows out. It's very runny lava, and it flows and flows and flows, and then eventually goes hard. And then the next layer rises up, flows and flows and flows, all down, creating this gently sloping volcano, and then goes hard. So over time these get bigger and bigger and bigger, and they can be absolutely huge. The reason they form like this is that the magma is runny and it travels a long distance. It's called basalt lava, and it creates rock. Rock is basalt, and this is what oceanic crust is made of. So at this plate boundary we have shield volcanoes because the plates move apart due to convection currents in the mantle. Magma rises from which layer? Well done. The mantle, forming shield volcanoes. And these volcanoes are associated with lots and lots of lava, runny lava, and they're not particularly explosive. Right, let's have an earthquake colour. On this plate boundary, we are going to see earthquakes, but they're small, smallish earthquakes. This plate boundary has the lower magnitude earthquakes, and that's very, very good news for the UK because this is our nearest plate boundary. So small earthquakes means no tsunami risk. The case study for this would be Iceland. And if we just have a look at the map we've seen before, this is a constructive plate boundary and it runs all the way up the middle of the Atlantic. And if you look at the shape of Africa and you look at the shape of South America, I think it's really clear to see that they used to be together, and over time they're pulling apart and they're pulling further and further apart. And if you fly from the UK to New York this year and then you fly that again in 10 years time, you'll be flying for a greater distance. So here we have a constructive plate boundary. Iceland here is on that constructive plate boundary, and we see volcanoes and we see that crust is being created at that point. Okay, that is number one, the constructive plate boundary. Let's have a look at number two. So number two is the conservative plate boundary or margin. And this is where the plates are not pulling apart, they're actually not pushing together, they're sliding past each other. They may both be going the same way but at different speeds, which has the same effect. So if I do a diagram looking from above, we can imagine one's going one way and one is going the other. Our example of this would be the San Andreas Fault in California in the USA. And if you have a look online, there are some great pictures of lines of trees that were planted in lines, and then suddenly there's offset all along a line, which is where the land has literally moved slightly. So what are we going to see here? What are we going to have? Are we going to have volcanoes? No. The plates aren't pulling apart, magma's not rising. Are we going to have earthquakes? Oh yes, we're going to have massive, massive earthquakes. So they'll have lots of small ones, but they will have big earthquakes. If you are living near a conservative plate boundary, this is what you need to be thinking about. Why? These plates moving along aren't quite like this. They're two jagged pieces of rock that are meshed together. And as they try and move past each other, they get stuck. So plates move due to convection currents in the Earth's mantle. The plates get stuck because they are jagged pieces of rock that can't slide past each other, like two bits of sandpaper. Over time, pressure builds. And the pressure builds up and builds up and builds up until eventually, in this example, maybe that bit there snaps off. So it snaps off here and it snaps off here, and suddenly they can move. So then there'll be the sudden slip, sending out shock waves. So these are called seismic waves. So let's just think again. The plates are trying to move. They're trying to move past each other, but they get stuck. The convection currents keep going. Pressure builds and builds until suddenly it slips into a new position. That slip is when the waves rush out in all directions. There's a little bit of terminology you'll need. So I'm now going to cross-section. So let's just put a tree there and a little house. Okay, so underneath the ground, if that plate's going that way, and that one's sort of trying to move past it in a different way. If that's where the earthquake happens, we call that the focus. And then the point directly above is the epicenter, and we tend to use that word more because we live on the surface, and that's the point that will get the first wave and the biggest waves, and the most destruction will happen here. And then these waves, just like throwing a rock into a pond, the waves will rush out. These wave fronts will rush out in all directions from the focus. So the epicenter will feel it first, and then they'll ripple away in both directions. The further you are away from the epicenter, the less, the destruction will be less. The waves will be less strong, but this is where it will be strongest. Okay, that's number 1 and number 2. Number 3, my personal favourite, the destructive plate margin or plate boundary. Okay, so let's just draw a picture. We have one piece of crust and it's going that way. This is oceanic crust, and at the other end of this crust it will actually be being created. So if we bring in our constructive plate boundary over here, you'll have it being created, and that plate will be moving along, and then at the other end this will be happening. So the oceanic crust is moving this way, and then it meets continental crust, land. That's where we live. Some houses on there. The oceanic crust is, unsurprisingly, under the ocean. So the oceanic crust is coming this way, the continental crust is coming that way. That tells us everything we need to know about what's happening underneath. There must be a convection current doing this and another convection current doing this. This is where they're pushing together. Like this. Now the oceanic crust is more dense than the continental crust. If you want some extra detail, this is because it's essentially basalt, which is an iron-rich rock, and the continental crust is essentially granite. That's a real simplification, but granite is a silica-rich rock, and it is less dense. So we are going to have earthquakes where? Where do you think they're going to happen? Yep, we're going to get earthquakes along this area here. So this is where this large lump of rock, jagged lump of rock, is trying to move this way, and the oceanic crust is trying to move this way, and they're going to lock here where the jagged rocks get stuck together. And again, exactly the same as the last one, we're going to have a situation where the plates get stuck, pressure builds, and then eventually it gets too much and you get the sudden slip. The rocks break where they've been holding on, sudden slip, and we get these seismic waves rush out in all directions. So the earthquake's going to be happening here, all along this section here. Now as you get deeper, we get friction. So if you rub your hands together and create some friction, what you'll notice is that your hands get quite warm. And the same thing happens here. So as these pieces of rock, and as we get deeper and it gets warmer as well, these combined effect, the friction at depth, leads to heat, which does what to the rock? What do you think this represents? Okay, so we get friction, which leads to heat, which creates magma as the rock melts. The rock melts and we get magma. So this magma forms at this point between the two plates. This magma is really different to the magma we talked about at the constructive plate boundary. If you remember, this magma was rising up from the mantle. So it was supplied by the mantle. This is not coming from the mantle. The mantle's down here underneath the crust. This magma is a bit of melted oceanic crust. It's a bit of melted continental crust. There are all kinds of there's water and carbon molecules in here, and these get into the magma. So this magma has a very, very different characteristic than that magma that we saw at the constructive plate margin. So here, living up to its name, the volcanoes are very, very explosive. And that's again because they are full of these volatile substances, and essentially there's gases in there, and it's very volatile and very explosive. So these are massive, very scary volcanoes, and they are called stratovolcanoes. Don't tend to get anywhere near as big as a shield volcano because they blow themselves to pieces. So let's just put a few notes on that one down here. So if I draw a stratovolcano, we can see that they tend to have a crater in the top, or a big gap really, where they probably blew themselves up last time they erupted. We're going to get a lot of ash and ash clouds in an eruption. This is ash. We might get a great big pyroclastic flow. Extremely dangerous avalanche of gas and ash and great big lumps of rock, and it comes down the mountain on a sort of a bit like a hovercraft on a cushion of hot gas. Very dangerous. You might get lahars, mud flows, coming down the other side or coming down this side. You'll certainly get a lot of ash. You won't see a lot of lava, but you might see some lava bombs flying through the sky. So very, very different, very, very dangerous. This is the stratovolcano, and the lava here is andesite. Again, this is there are many different types of lava. The main one would be andesite. Interestingly, we can link that back to our map here, because this is the Nazca plate, and the Nazca plate is going that way. This is the South American plate, which is going that way. So this Nazca plate, the oceanic crust, is going underneath the South American plate, which is land, continental crust on that side. And that's why we have a mountain range all along here called the Andes, and a lot of volcanoes, because it's exactly this situation. So the Nazca plate is going underneath the South American plate, creating volcanoes, and the land gets pushed up into mountains. And the reason it's called andesite is that it's seen in the Andes. So let's just review. We have 3 plate boundaries: constructive, small earthquakes, shield volcanoes, runny lava from the mantle. Conservative plate boundary, big earthquakes, because the plates get stuck, pressure builds and suddenly they move. Destructive plate boundaries, plates get stuck here as they push into each other. The more dense crust is pushed underneath the less dense continental crust. Earthquakes, big earthquakes along here. Big earthquakes. And then we get melting here. Very different type of lava rises up to form these stratovolcanoes. We'll just put an example in. A good example for a destructive plate boundary is Japan, and the Sendai earthquake we're studying formed a destructive plate margin. The conservative plate boundary was San Andreas, and the constructive plate margin is Iceland. 3 plate boundaries. You will be asked about one of those in the exam. Well done.